Good afternoon, and thank you for joining me on this webinar about SOLIDWORKS Simulation Premium, and specifically about nonlinear simulations. My name is Philip Morrow. I'm based out of our Austin, Texas office, and I'm one of the simulation specialists here at MLC. I've been here almost 6 years, so you might have talked to me on a tech support case in the past or heard my voice in other videos, or maybe you've met me or will meet me at one of our trainings or events. So I like to put a face out there with a name, but I don't really want to spend any time on the background of the intro. I'd like to jump straight in to nonlinear simulation talk, and specifically, what are they, how do we identify them? Because we need to know when we're looking at an FEA package, a structural simulation package like this, do we need the highest level? Do we need to go to simulation premium? So I want to show you some of the more common examples I see that push people towards running a nonlinear analysis instead of just a linear static. Then I want to show you a couple of examples. A classic small displacement versus large displacement analysis, what that means and why you might go towards nonlinear instead of just activating a large displacement flag in your linear static analysis. I'll show you that with an example in the software and a bit of how I set it up. And then I want to move to something with intermittent fixtures. This is great for snap fit joints, or really any condition where you might need to vary the loading, turn one load off before another, turn something that's fixing something down off after a certain amount of time. So let's start out with identifying some of these nonlinearities. And if I can pull them into a couple categories, the first one I see is geometric. This really comes up with small displacement versus large displacement and a couple other times. But the way I think of it is the response of something. Do I need it to stiffen up? If I push on something, does it need to give me more spring back the more I push on it? And does the direction of my loading need to change as this thing deforms? Of course, the material is a big reason people might move to nonlinear or even simulation premium. If you're working with composite materials, maybe something that has a layup, could be carbon fiber or fiberglass type composition, that's going to be available in the simulation premium license. But really any material that we can't consider linear, something where if you put in 1 inch or 100 pounds and it bends an inch, 200 pounds does not mean it's going to bend 2 inches. Well, that's a nonlinear response. So there's a lot to look at when it comes to materials. And then the third one is something that can be a little hard to figure out. So I hope to show you an example of this in action, and that's the difference in contacts. When two items are contacting each other, and that contact area changes a lot over time. If you're really developing your own threads, threaded connections can have this. Certainly gear teeth, when they connect together, have a complicated contact area that's changing as things move in the simulation. So we'll look at some hands-on examples of that to give you an idea. But first, before we go there to the hands-on examples, let's talk a little bit deeper about these three. The first being geometric nonlinearities. Or this is also what could be called the difference between small displacement and large displacement. Perfect example of this is a cantilever beam, or even just a diving board. You know, if you're saying, oh, we'll look at a diving board and we'll put, 100 pounds out at the end of it and it's going to move down 5 inches. Maybe 200 pounds is going to move it 10 inches. Maybe that linear response holds for a while. But as soon as you put more on it, we know that diving board gets much stiffer and it gives you more spring back. And it needs to stiffen up to give you the proper answer. That is a nonlinear response in itself. But the other thing that's happening at the same time is the direction of the loading needs to change. Initially, the force arrows or your weight on a diving board is going straight down. But as soon as that starts to bend a relatively large amount, those arrows aren't going straight down anymore. So to update that type of force input, that's also a nonlinearity. Now, it could be more complicated when it comes to geometric nonlinearities. When you push on something, it might give you more spring back. Or if you think of a metal, you might push it well past its yield point, so it starts to permanently bend, and then all of a sudden it softens, and you can bend it a lot easier. So a little bit more weight makes it bend a lot further. And that also would be a geometric nonlinearity. Above that, we come to the materials. In the materials, I try to just break it down to Hooke's law. Now, Hooke's law is kind of what I've been explaining as a linear response. So for a little bit more stress, we get the same amount more strain. 100 pounds moves at 1 inch, 200 pounds moves at 2 inches. But at some point, if we think about the materials we're all used to, maybe metals or ductile materials, at some point they start to bend permanently, right? And at that yield point, it only takes a little bit more force to move them a lot more and see a lot more strain until ultimately they fail. Now that's in the material model itself, but the first place I look is, would we have a different response based on how we're loading things? For instance, if you hold a load onto something for a very long time, does it start to get creep or viscoelasticity? That type of behavior from holding something a long time, or maybe something even work hardens and gives you a difference there. Or thermoplasticity, if things soften and change and get more strain as they start to heat up. Now, some materials behave this way on their own. If you deal with a rubber, it's just not going to have the same stress strain curve that a ductile material like a metal will. So in SOLIDWORKS Simulation Premium, we do have about 6-7 different material models here. The elasticity model, the linear elastic is what we use in most static analysis. We have other elastic models like the elastic plastic model, and also the von Mises plasticity models. We have a linear viscoelastic model and a creep model, but I think one of my favorites, it's actually what you're seeing a material curve for here in the bottom right, is the nitinol model. Nitinol is really cool. If you look at that curve on the right, you can see it behaves differently when it's loading versus how it's unloading. It behaves differently when it's in tension versus compression. Even when it changes thermal properties, it's pretty different. In fact, if you're into looking at nitinol, I would highly recommend checking out this video on YouTube. It's from the channel Engineer Guy. I have no affiliation with this channel, but it's just really cool. It's called Nitinol, the Shape Memory Effect, and Superelasticity. It's quite an interesting material, and we do have a curve built into the software for that. So if you're working with those types of materials, whether they're exotic or they're just plastics and rubbers and gasket material, that's a common reason to move to a nonlinear solver. Now, the third type is the one I said that maybe was a little more complicated, and that's those contact nonlinearities. Imagine just dragging something along a table. You might change the amount of contact the table has with that item, and the friction there is changing and the surface area between those two things are changing. Well, the nonlinear solver can really work with this all the time by incrementing the load that we're dealing with. So I want to introduce the concept of pseudo time. We might say that a nonlinear analysis happens from 0 to 10 seconds, but those seconds, they're not really the wall clock time. We could just call them pseudo time. In this way, we could say, all right, in 1 second, let's put on 10% of the load. And we can measure the response there, the displacement after 10% loading, and say, okay, now based on that, maybe the direction of our load needs to change because something's bent a whole lot. Maybe we need to update the stiffness so it gives us more spring back, or perhaps we're at a really different place in its material curve. So we need to update all of those things kind of in an iterative process, and then we can move to 20% and call that 2 seconds and have all that updated and measure again. So this is how nonlinear solvers can deal with contact problems, and really the pseudo time curve is fundamental to dealing with a lot of nonlinear problems. So I hope those 3 areas give you at least an idea, a rough idea of the common reasons I would see to go to Simulation Premium and how you could identify them a little bit quicker. I'd like to move to a hands-on example that perhaps shows these in a more tangible way. And the first of that would be small displacement versus large displacement. When we run a linear static analysis, we make a small displacement assumption. We assume that things haven't deformed so far that we need to update the direction of the loading and the stiffness of the material itself. So I've got an example here in SOLIDWORKS, which is just a hose clamp like you'd put on the end of any rubber hose and tighten down. And I'm going to run a linear analysis here first. For this setup, I've simply given it a material. This is a AISI 304. Notice when I'm looking at materials in the linear analysis, I only need a couple of material properties, one here in red, and I can really only choose between 2 linear elastic models, either isotropic or orthotropic. In this case, instead of putting a force on here, what I've done is I've fixed my hose clamp at one end, so I'm going to say, well, let's keep that face, that end of it constant, but I decided to turn the other end. I want to wrap it all the way around a hose. So that's going to be a pretty large deformation. In order to do this, I'm just using a prescribed displacement. This is a fixture, but instead of leaving the fixture at 0, I simply put in 6 1/4 radians. It's roughly 360 degrees to turn that face around. And then I ran this. This runs pretty quick, but I want to show you the results I got. So when I first switch to stress results, I think, well, that doesn't look like 360 degrees, but the deformation is pretty small. So maybe I should start with displacement results. One thing I see is that the stress here is way above the yield strength of the material. I can tell by the red arrow right away. I'm going to have a factor of safety below 1. The thing seems very broken. And that would happen if we continued along a linear curve and didn't account for any of that permanent deformation. So let's check out displacement. And this has a deformation scale of 1. So this is the true scale calculated into this long shape. What's going on? There's no way that that turned around 360 or that that's the shape I meant to make. Well, remember, those loading directions really don't change. So while I told this thing to rotate, it really just kept moving straight down here. Just like if I put a force on the end of a diving board, but never moved those arrows. So you just went straight down. So that's not going to work at all. I want to show you something else about this study when I run it. Because normally I wouldn't have even got this far. I'm going to run this right now. And then immediately I get this message. Excessive displacements were calculated in the model. This is SOLIDWORKS realizing that we're breaking the small displacement assumption. It's saying, hey, these things are moving so much, we think you should be updating material stiffness. We think you should be probably changing the loading direction. If I hit yes here, it's actually going to try and do that, and the solve will take much longer. So I'm not. 9 times out of 10, if I see this in a static analysis, I forgot to put a fixture on something or a contact set, and literally something's just trying to fly away. And I can say, no, just continue with the small displacement assumption, and then these are the results I'm going to get. Now let's say I hit yes on that message. If I hit yes, I'm going to get a study that looks like this. My setup is exactly the same. It's still a linear static, but I'm going to go into the properties of this study, and notice this large displacement box is checked. That's it. If you hit yes on that excessive displacements message, it is going to check this large displacement box, and it's going to get rid of that small displacement assumption. It's essentially going to be a nonlinear solver. It's going to update material stiffness, and it's going to update those load directions, but it's going to take a lot longer to solve because it's going to start iterating on that pseudo time curve. Now when I finish this same analysis just with yes on that message or by hitting the large displacement flag there in the options, I do get the results that I was expecting. This thing curled all the way around. When I look at my stress results, still pretty high, but I've got a super small deformation. I think if I put that on true scale, you'll see this as well. And I knew I was permanently deforming, so at least I got the end result here in deformation that I was looking for. How about if I animate this and watch it curl up? Well, actually, it doesn't curl up at all. This animation only knows about our start, which was flat, and our end, which was a loop. So this animation is definitely wrong. That's not the way I would curl this thing around a hose. It looks like it flies right through each other. So I only know about the beginning and the end. And so it's really not giving me what I want. Further than that, if I had something more complicated here and this thing failed to run, failed to converge for some reason, I really wouldn't have any more controls over that. So I know now I need to use a nonlinear solver, which is pretty easy to do. I can take one of these studies and copy it and just choose nonlinear. That's the easiest way. I'll have the exact same setup. I could also drag items from the tree onto the study tab of other studies down here to copy just those parts. And so this setup hasn't really changed at all, but this is using that iterative time curve here, that pseudo time, to give me results. And they should be the expected results right away. And not only that, I get the correct intermediate results. So I know how this got to be wrapped up. Just playing the animation, I can see, okay, we know every incremental step along the way, and we can look at the results at any of those spots. In fact, I'm going to hit run on this. I'm going to run this one as well. It's a nonlinear study, and SOLIDWORKS tells me, hey, you chose to show intermediate results. So even as it solves, I can see how this is going. You know, a nonlinear study can take more time to solve for sure. You're getting a lot more information out of it. You're making a computer work harder. So it's really nice to get these intermediate results and know things are going the right direction without having to wait until the end. Or if you cancel a simulation halfway through, you can save your results up to that point to give you an idea where to go next. So I hope that gives you an idea of a common place to see the difference between small and large displacement, and certainly what that excessive displacements message means. 9 times out of 10, if you're in linear static and you see model is unstable, the iterative solver is stopped, or the excessive displacements message, probably something doesn't have a fixture or doesn't have a contact set, and it's a good time to just stop and review those things and hit no. But if you know you're breaking one of those small displacement assumptions, you're getting this geometric nonlinearity, maybe hit yes on it, or maybe go all the way and copy it to that nonlinear study. So that's probably the most common nonlinearity I see, besides maybe someone knowing they have a nonlinear material model they need to run right off the bat. The next one I'd like to take a look at, though, is harder to identify. And this is that contact nonlinearity. Certainly I can pick it out quickly if we're talking about a custom complicated thread connection, or something that has sliding press fit or needs to permanently deform so that it yields beyond its permanent deformation point in the material curve. Those you can see pretty quick, but sometimes these contact conditions are not as easy to see. So what I've got is something that clips together. It's a couple plastic components, they're ABS plastic. You would push one together and it would snap into place. Well, one of the cool things about using a nonlinear model here is that we have that pseudo time curve. We can turn things on and off. We can have one event happen before another. Another nice thing to go Sim Pro or Sim Premium is that you can break things down to 2D. In this case, I have some good symmetric assumptions, so I actually set up a 2-dimensional nonlinear study here because it's going to solve much faster. I really haven't changed things in the materials too much, just used a plastic. And again here, I haven't applied any external loads. In this case, I decided to just be slick again and just use fixtures. So let's take a look at the fixtures I've set up. On one side, I've got a component that I don't want to move. I want this one to be held in place, so I'm just grabbing this edge and not letting that move at all. Of course, this is actually cut in half, so I did need to apply symmetric fixtures on here to say, hey, these edges cannot move up in the Z direction. But what's more interesting here is the reference geometry fixtures I put on here. These are often called prescribed displacements. Again, it's just a fixture where the value is not 0. Although since I'm using a nonlinear solver and I'm using a time curve, I can describe how this varies with time. And we'll just view the curve that I've typed in. The default here would be to go from 0 to 1. And it's 0 to 1 seconds, but it's that pseudo time, so it's not wall clock seconds. But what I've done is push this forward in the X direction until it gets to the point that it should be snapped together. Then I'm going to have it hold in that position for a short amount of time and then retract back to its starting position. You can do this with any force, any loading. Here I'm doing it with a fixture. In fact, I've got another fixture here because after this clicks into position, it makes it over that hump and bends and does all the friction and slides over that. In order to release it, I need to give an upward force. So you would normally push that in with your thumb. So that's what I've done. I've got a fixture here that is completely off until just after 60% of this simulation, or 0.6 seconds here. It's clipped into place, and then for a brief period of time, I need to give it enough force, or really need to give enough translation to clear that component, and then come all the way down and just turn that fixture back off because it's not needed for the rest of that simulation. So this is 2-dimensional. It runs pretty quickly. Again, I can watch intermittent results, but I just want to show you the animation here so you can see how my different fixtures have affected things. This is definitely a nonlinear contact. We certainly have a large amount of motion. It would probably trigger a large displacement flag if we ran this other ways because of how far it's moving. But I also have this ability to turn on and off loads and on and off fixtures over time and deal with this more complicated contact until there's a lot of friction there, there's a lot of things changing, and then all of a sudden it quickly releases. Using a pseudo time curve and a nonlinear solver gives us the ability to manage that. So if you're interested in Simulation Premium, whether it's for a material model, some sort of nonlinearity in your simulation, maybe it could be a contact or just large displacement, let us know. We're happy to talk about these beforehand and make sure you're getting the right tool for the job. 99% of things can really be solved in linear static, but when you need to really form something permanently, when you need to deal with a complicated thread connection, that's when you might start thinking about nonlinear. I want to mention just quickly the 3 different packages of simulation. You might already know that if you buy just a CAD SOLIDWORKS Premium, that actually comes with a linear static solver, but there are sim licenses just on their own. There's a standard, professional, and premium. Today I just wanted to talk about nonlinearities and using that solver, but in addition to that, you can deal with composites in any of the linear static study types as well, composite modelings. Dynamics are here as well, linear and nonlinear dynamic, as well as dynamic fatigue. So all of that fits inside of the simulation premium model. Whichever one you get into, don't forget about training. We offer that for every single license type, but no matter which one you're doing, I highly recommend coming to our Simulation Essentials class, dealing with the mesh, feeling confident in your results, understanding that for the inputs you gave it, you're getting good outputs. All of that we cover in just 3 days. It's a lot of content, but you can come spend that with me, and I'll make sure you feel good about the simulations that you're running and the results you're getting from them. If you have Simulation Professional, which I would say is probably our most common simulation license type, stay all week. We just take all of those fundamentals we built in those first 3 days, and then we move that to 2 more days and cover all the different study types that are in the Simulation Professional license. And we have training classes just like that for nonlinear and for dynamics as well. So again, thank you for the time. I appreciate it this afternoon. If you have any more questions, please type them into the chat or reach out to us here at MLC. Myself or any one of the team of experts who's here on simulation would be happy to help. Thanks again.